Okay, why don't I get started? Hi. So I wanted to, so Alice, actually, does Student Learning Center start next week? Does Student Learning Center drop-in tutoring start next week? Okay, so I'll at least say that. And is it 9 to 4 Monday through Thursday and 9 to 12? 10 to 4 and 9 till, or 10 till 12 on Friday? Is that right? Oh, there's no Friday? Okay. So I just want to say a little bit about the Student Learning Center since it's starting next week. They're starting drop-in tutoring. I think this is a very valuable resource for you. The Student Learning Center offers drop-in tutoring through tutors that have taken a class using your book before. A lot of the tutors I know are, excellent. Some of them are my ex-students. So Alice, who I was just talking to, did very well in my class last year, and she tutors there. And do you actually? I'm sorry, Alice, to put you on the spot. Do you have a study group scheduled? I'm sorry, Monday 5 to 6. Monday, Wednesday 5 to 6. Okay, but so it starts this coming Monday. Okay. I'm sorry, let me write down the drop-in tutoring first. So the drop-in tutoring. Oops, I already said that. Drop-in tutoring, Monday through Thursday, 10 to 4. And it's in the Student Learning Center atrium, which is the Cesar Chavez building, just on, I guess, the north side of Lower Sproul is the Cesar Chavez building. So okay, the Cesar Chavez building, where the Student Learning Center is, and then the study group for this class. And do you have a room for that yet? Okay, so go to slc.berkeley.edu if you want to find out the room. And Alice, actually, if you can email me when you find out the room, I'll put it on BSpace. Okay, so there's a study group starting Monday, Wednesday, 5 to 6. That's location to be announced. Okay, I think a lot of people view the Student Learning Center as somewhere to go when you're not doing so well. And certainly that's one use for it, but I think it's also a place to go if you really want to excel in the class. Okay, so a lot of students that go to drop-in tutoring and to the study group are not going to be students that are like just trying to pass the class, but like I say, students that are trying to do really well. So, regardless of what your level is in this class, I think you can benefit from the help that you'll get either in drop-in tutoring or in the study group. Also, both are ways to sort of network with fellow classmates, find people to study with for exams, all that kind of stuff. So if you go to drop-in tutoring, they'll kind of group you with other students from the class, and you can talk to each other. I think teaching other people the material is often a good way to learn it like cold. So if you have an opportunity to explain things to other people, I think that benefits you also. Okay, so that's a little quick plug there. Okay, so I wanted to talk about any questions about Student Learning Center or anything? Okay, I used to work there, so that's part of my bias, I think, is that I think it is a really good place to learn things. It's louder than usual. Is there something going on that I need to know? Okay, all right. Okay, so this summation handout I started talking about on Tuesday, and I apologize for not getting it up. Tuesday when I tried to put it up, the BSpace was down, and then I sort of had checked it off mentally as something I had done, and then I hadn't done it. Okay, so you may not have gotten a chance to read it. I'll go through it, so there's no problem there. So I started just talking about a list of numbers. So a list of numbers. In general, I'm talking about the summation handout. So you can write a list of numbers like this. I mentioned on Tuesday that if you want to add them up, you can write it like this. Okay. So what this capital sigma means then is that we're adding up a bunch of things. And the first one is when I equals 1. So that term is x1. And then we just continue. Let I equals 1, 2, 3, until we get to the last one, which is when I equals n. So that's the xn term. So that's a way to add up all the numbers. You can write the average of a list of numbers as what you get if you add them all up, divide by how many there are. And that's often abbreviated x bar. Okay? So that's how you write down the average in summation notation. If we do this for a specific list, you might imagine that I have just the numbers that I was dealing with before, 1, 3, 4, 5, 7. And you can think of them as being like x1, x2, x3, x4, x5, more kind of generically. So if I wanted to write down the sum of them in this way, this would literally mean x1 plus x2 plus x3 plus x4 plus x5 divided by 5 would give you the average. Okay? So okay, the fourth number on the list, what this means is the fourth number on the list is 5. Okay? So like I say, you know, if you wanted to sort of generically write down formulas, that provides me with a kind of shorthand way of doing it. Okay. So for this list, I already calculated the average before. The average is 4, but I wanted to just give you a slightly more concrete example. If you want to find the, you know, some more complicated formula, here I just have kind of the numbers themselves, but I can do things to the numbers and then add them up. So for example, if I want to square the numbers, what I would do is to just write down x1 squared, x2 squared, up to xn squared. If I want to take the sum of the squares, that would look like this. Okay, so the first term in this sum, right, again, this sum means add up whatever this is, starting when I equals 1 and then finishing when I equals n. So the first term in this sum would be x1 squared, and then x2 squared, and all the way up to xn squared. Okay, so again, that's sort of a generic way of writing down the sum of the squared values. Okay, so now where I'm sort of building from this is to think about the standard deviation in these terms. Before I do that, though, I want to just discuss a few properties of sums. So I have these listed on the handout, but I think it is worthwhile talking through what they all mean. So the first one, the first property I have listed is what happens if you add up a constant value. So adding a constant value, or summing a constant value. So what I mean by that is this. So I'm treating this as a sum from 1 to n again. But what I'm going to write down is a c there. The c, you know, represents some number, but it doesn't have a little I subscript. So what do I mean by that is again, I'm summing from I equals 1 to n. So they're going to be a total of n terms that I'm adding up. The first one is when I equals 1. Well, when I equals 1, this thing is just c, right? It doesn't change when it doesn't have different values. So the first term is a c, second term is a c, third term is a c, and so forth. I have n of these that I'm adding up. So if you add up the same thing n times, that's n times whatever value it is you're adding up. Okay? So if you want to add, if you look at what this says in terms of summation notation, again, for the other sums I've done, there's some I here. So when I has a different value, this thing is a different value. Like if you imagine my numbers being x1, x2, x3, x4, x5 up there, when I equals 1, then xi is equal to 1, just x1 and x2, x3, x4, x5. Here, like I say, when I changes, there's no I here, so I'm just adding up the same thing over and over again. OK? Any questions about that? OK. So second property is actually, let me. So I don't know if anyone remembers what the distributive property is in general. What it is it's if you are adding up things that look like this, I equals 1 to n of a constant times a value that changes. Okay? So if you think about what that means kind of in longhand, that's c times x1. That's the first term, right? When I equals 1, I get cx1, cx2. Add them all up. The last one is cx sub n. And the distributive property in general means basically that you can pull the constant out. So that constant c does not, it's not different when I change the value of I. It doesn't change. So I can pull that out of all the terms, and I get this. Oops. OK? And then that finally is c times the sum. I equals 1 to n of xi. All right, so that's what's going on there. What I'm saying is that if you have a constant that's multiplied by every single term in your list, you can pull that constant out in front and multiply the constant by the sum at the end. So one thing you might think about that, what one use for that or something might be if you have a bunch of people's weights measured in pounds, or say you have them measured in kilograms. Then if you want to convert into pounds, you multiply the weight in kilograms by 2.2. So for each person, weight in kilograms times 2.2 would give the weight in pounds. Now, if you wanted to, you could convert every single person's weight into pounds and then add them all up. That's kind of what this would be saying, right? For each person, multiply by 2.2, take their weight in kilograms, multiply by 2.2, go through everything. But you might as well just add them all up and then multiply by 2.2 at the end. Right? If you have the sum of all the weights in kilograms and multiply by 2.2 at the end, that would give you the weight in pounds kind of more simply, rather than multiplying every single value by 2.2. OK, any questions about that distributive property? OK, so the last property I'll be using is called the commutative property. So this has to do with things that look like this. Okay. So we have xi plus yi, and we want to add up all those things. So if I want to add up all those, the first term looks like x1 plus y1. The second term looks like x2 plus y2, and so forth, up to xn plus yn. And that's going to be equal to, I can regroup all the terms, right? So I can regroup all the terms so I have x1 plus x2 all the way up to xn. Just pulling the first term from each sum, and then plus y1 plus y2 all the way up to yn. And that will be equal to sum of all the x's plus sum of all the y's. Okay? Sum I equals 1 to n of xi plus sum I equals 1 to n of yi. Okay? So I don't know, if you imagine a bunch of salaries of couples, and you want to find out what the total salary is of all the couples, you could add up all the salaries of like one person in the couple. Or you could add them all up together, or you could add them all up separately. All the salaries for one person, all the salaries for the other person, and then add it all together at the end. So, you know, however you wanted to do it. If you had the data in one particular form, then it might be more natural to do it that way. Okay? Questions on that? Okay. So those are the properties of the sums. And let's see, I want to talk about, okay, so now I'm ready to talk about standard deviation. So remember SD, standard deviation, is equal to the RMS of the deviations from average. Okay, so mathematically, or in terms of sums, how can we write that? Well, we're taking the RMS of deviations from average, so let's kind of go through step by step what that means. Deviations from average are differences between actual values and the average. So those deviations from average will look like this. You have some kind of generic value, the value for the ith person. Subtracted from that, we have the average. So that's a difference between a value and the average. And I want to find the RMS of those. So the RMS of those is what I get if I square them and then take the mean and then take the square root. So if I square them, I'll just kind of generically write down what a squared deviation would look like. You just take the deviation and square it. And then I want to take the mean of those, or take the average of those. And the average is what I get if I add them all up and divide by how many there are, right? So I want to take a bunch of things that look like that, add them all up, divide by how many there are. So mean is take these values, and this is a slightly complicated formula, but this is just a value that depends on I. For every value of I, that's going to be different. I'm adding them up from 1 to n and dividing by how many there are, n of them. And then finally, to take the RMS, I want to take the square root. So that is just rewriting that same thing. Sum I equals 1 to n. Sorry, it's a little crowded. Sum I equals 1 to n of xi minus x bar squared divided by n. Okay, so that's the SD. Okay, so that's one way to write the standard deviation in summation notation. Any questions on that? Okay, so in practice, this would sort of lead you to the same situation or the same thing as using the formula that we did before. It's literally the same thing, right? If we take the values, subtract off the average, square them, add those all up, divide by n to take the square root, that's the same calculation we would have done before. So I'm going to give you a different formula for the standard deviation, which is a little bit simpler in practice. So I'm going to go through a slightly messy derivation of this other formula. And it might seem a little scary. I won't ask you to reproduce what I'm about to do or prove things in general. But I think you should be able to follow it, first of all. And second of all, you will use the steps that I'm going to do in different ways, in different contexts. So like I say, you won't have to reproduce what I'm going to do. I think it's hard to think of the steps that involved in getting from this formula to the other formula, but you should be able to follow it. Okay, so second formula. for SD. So I can start with that formula. I'll just rewrite it. So SD is equal to square root of okay. So literally this is the RMS, the deviations from average. So I take the deviations from average, square them, take the mean, take the square root. And I want to expand that. So I'm going to expand this sum. Okay. So you can think about doing FOIL on this, or however you want to think about it. Get the first term squared, xi squared, and then we're going to get 2 times the product. So the product is xi times negative x bar. 2 times that is the middle term, and then the last term is just negative x bar squared. Gives us positive x bar squared. Okay. So from there, I'm going to use the third property, the commutative property, for 3 things. So the 3 different terms here. And I'm going to split them all up. So I'm going to write this as the sum of xi squared over n. All these sums are 1 over n, are from 1 to n, but I guess I'll keep writing it. The middle term is going to be, I'm going to write this as plus, and then the things I'm adding up are going to be negative, just to make it clear what's going on. Okay? So I'm just splitting up the sums. I have like this first sum, and then the second sum, and then the third sum, and I'm putting them all over n separately just to make them separate terms. Okay? So first term, second term, and then third term. Okay, so again, that's the commutative property. I guess I'll write that. Commutative. Okay, so I split that sum into 3 different parts, and now I want to deal with each of the parts separately. I'll actually leave the first one alone. Okay, so that's just the first term up there. And now the second term, I want to pull out the constants. So the distributive property tells me that if I have any constants floating around with the xi, I can pull those outside. So -2 is a constant. X bar, the average, doesn't depend on the value of I, so that's also a constant. So I'm going to pull out the -2 x bar, and then I'm left with the sum of xi from 1 to n over n. Okay. And then this last one, so x bar squared is itself a constant. So if you want, you can think of that as adding up that constant n times, right? When I change the value of I, that doesn't change. So this adding a constant property tells me that that's the same thing as n times x bar squared over n. And the n's are going to cancel. OK, questions on either of those steps? So the first step here that I'm doing to this term is to pull all the constants out in front. And then here I'm using this property of adding up a constant n times. The sum is n times x bar squared, and then I'm dividing by n. OK, questions? OK, so then again, just leaving that first term the same. What's going on with the second term? Anyone see anything I can do to make that simpler? Yeah. This is not a so her comment was that well, that's not into the sum anymore, right? I pulled that out of the sum. So I'm thinking about something I can do with that. Yeah. Yeah, this is the average, right? This is what you get by adding them all up and divide by n. So that's the average. So I have -2 x bar squared, right? Because this is average times the average. And then over here, these n's cancel, and I get plus x bar squared. So this is, I went through all this work just to get this little bit of cancellation here. Okay, minus 2x bar squared plus x bar squared is just minus x bar squared. So this gives me another formula for the standard deviation. And it turns out this formula is a little bit easier to deal with for doing calculations and also for doing some manipulations that you'll do on this homework assignment. So when you can, I would use this. The reason why the book does the other formula, I think, is that it makes a little bit more sense intuitively. If you're interested in measuring sort of the typical deviation from average, it sort of makes sense to start with that and do some calculation based on what those deviations from average actually are. RMS of deviations from average is a reasonable way to sort of think about the standard deviation. This does not have any good intuition behind it as to why this calculation should measure the typical deviation from average in any way. So that's why the book emphasizes this, that the book gives this formula kind of tucked away in a technical note. But yeah, mostly this is a formula that was sort of separate from the book. Okay, so like I say, this is a little bit easier to use in practice if you want to do calculations. So I'll do one really quick, and I'll show you that it is a little bit easier. If you want to remember this formula, you can remember it by thinking of it as the square root of the average of the squares minus the square of the average minus square of average. Okay, so if that helps you remember it, you can use that. Okay, questions? Yeah. From this to this? So this in parentheses here is x bar. It's the average. So I have negative 2 x bar times x bar. There. I think that is probably the weirdest looking step in there. If there's a trick to this at all, that's the trick, is to sort of recognize that sum is equal to x bar. So we get that little bit of cancellation at the end. Yeah? Yeah, so this term here means that I'm taking x bar squared and adding it up over and over again. X bar squared plus x bar squared plus x bar squared n times. So, yeah. Okay, any other questions? That's the other tricky step, I think. Right? Alrighty, so let's do it. Let's do an example. I'm just going to use the same numbers I have up there, 1, 3, 4, 5, 7. You remember I calculated the standard deviation of those yesterday or Tuesday. So if you want to find the SD using this formula, what you're going to do is do this. So these are the values themselves squared. So one thing that makes this formula nice is you don't have to go through the work of calculating the deviations from average for every value. So you can immediately just jump to doing 1 squared plus 3 squared plus 4 squared plus 5 squared plus 7 squared. Divide that by 5 and subtract the average. Average of these is 4 squared. Okay? So you can kind of get this advantage of dealing with the numbers themselves in this sum rather than deviations from average. OK, so this is 1 plus 9 plus 16 plus 25 plus 49 divided by 5 minus 4 squared. And you might possibly recognize there is a pretty strong similarity between this calculation and the calculation of the root mean square. If you remember me doing the root mean square last time, it's that, okay, without the subtracting of the 4 squared there. So if you want to think about root mean square in general, it's this, right? Take the values, square them, take the mean, take the square root. So this second formula for the standard deviation also looks a lot like the RMS formula. Okay. So 1 plus 9 is 10, plus 16 is 26, plus 25 is 51, plus 49 is 100. So we get 100 over 5 minus 16. 100 divided by 5 is 20, minus 16 is 4. So square root of 4, which is 2. OK, so like I said, I did that calculation of the SD on Tuesday, got the same thing, but this is a little bit quicker. All right, questions on that? OK. So that's not the only use of that other SD formula. See, how am I doing here? OK. So another thing you can do is what's called change of scale. And the book discusses change of scale in chapter 5, and I kind of skipped over it because I like to talk about it once we've already done a little bit of stuff with summation. So change of scale is what happens if we add a constant to every number in a list, or we multiply every number in a list by a constant. And what we're interested in is what happens to the summary statistics. So change of scale. So basically, two things I'm curious about. Adding a constant to each value in a list and multiplying each value in a list by a constant. And I'll divide this second one into two parts based on whether or not that constant is positive or negative. Positive constant and negative constant. So in these different cases, what I'm curious about is what happens to the summary statistics. OK. So first one, adding a constant to each value of a list in a list. So like I said, I'm curious about what happens to the average, the median, the standard deviation if I do this. So what happens to the average? Well, if you add a constant to each value in a list, you sort of have intuitively, if you want to think about it in terms of like a histogram, what you've done is you've shifted everything over. So the balancing point will shift over by the same amount. So I'll do this really quick with my numbers 1, 3, 4, 5, 7. Suppose I add 3 to each value. So then I get 4, 6, 7, 8, 10. OK, so they turn into 4, 6, 7, 8, 10. The average now is going to be 3 more. And you can kind of just think about that in terms of the center, 4, change it into 7. If you want to think about that in terms of the histogram. I'm not going to do the whole histogram. I just want to sort of show the picture. OK? So if you drew a histogram of these numbers, it'll look like this. I haven't done a y-axis or anything, so it's sort of not complete. But in terms of just illustrating what the balancing point is, there's sort of enough to do it. So the balancing point is here. If I move all the numbers over by 3, 4, 6, 7, 8, 10, basically everything's just shifted over, right? So now it'll balance at 7, okay? So whatever I do, add a positive constant, negative constant, shift over that picture right or left, it's going to change the average by that amount. So the average goes up by 3. The median also goes up by 3. So I think that's fairly obvious too. If you just shift things over right or left, that's what's going to happen. So the average and the median go up by 3 in this case. In general, they go up by whatever the constant is. Okay? So in general, average and median go up or down if it's a negative constant by whatever the constant is. And by constant, I just mean whatever number you're adding to each number on the list. Okay, questions about that first part? Okay, so let's think about the SD now. Oh, I'm sorry. Yeah. So since I've talked about summary, since I've talked about summation, let me show this one really quick in terms of summation notation. So in terms of summation notation, what's happened for the average is that originally it's this, right? I equals 1 to n divided by n. Okay. So the new average after I add 3 to every value. Actually, I'll do in general. If I add the same constant to each number in this list, the new average is this, right? This is the old value plus whatever number that is. I'm doing the same thing to every number on the list. And so I can use the properties of the average to figure out how much the average is going to go up by. So splitting this into 2 sums, I'm going to get sum of xi over n. This is whatever the old average was, plus sum of whatever the constant is divided by n. Well, one way you can think about this is it's like the average of a list of numbers where every number on the list is that constant. So the average of that list must be that constant. If you want to actually do the math, that sum is going to be n times the constant, right? If you add up a constant n times, you get n times the constant divided by n. So I'm going to get nc over c, or sorry, nc over n, which is just c, okay? So whatever the old average was goes up by that constant. Okay? So any questions about any of that? Okay, so there's sort of no summation way to talk about the median, but I think it's pretty clear what's going on. Okay, so then let's go to SDs. I guess I'll erase this. So for the SD, what happens to the SD? So a few different ways to think about this. I think the easiest way to think about it is to think about that first formula, RMS, the deviations from average, and think about what happens to the deviations from average. So deviations from average so before we add a constant to the list of numbers, the deviation from average is like xi minus x bar, right? The new deviations from average, well, the numbers have changed by the constant, right? Xi plus the constant. But the average is also changed by the constant. The average went up by the constant also. So in the end, the deviations from average are the same. So since the standard deviation is based on, maybe I should just say it this way. It's the RMS, the deviations from average. The deviations from the average themselves haven't changed. So any calculation based on those deviations from average is going to be exactly the same as the calculation we had before. So the SD is unchanged. Intuitively, if you think about that, if we think about our picture here, change the 1, 3, 4, 5, 7 into 4, 6, 7, 8, 10, the spread hasn't changed, right? the spread around the average is the same in each case. And it's the same idea, right? That the deviations from average are the same. Okay? So if we add a constant, not going to change the deviations from average, not going to change the SD. Questions, thoughts? Yeah? No? Okay. So that's that. That's all the stuff about adding a constant. Now let's multiply by constants. Okay, so 2 multiplied by constant. So first thing is if that constant is positive, so I'll do a quick example first. Suppose we have these numbers and we double them all. So multiply by 2. That changes it into 2, 6, 8, 10, 14. So you can kind of see intuitively that the center value is getting doubled, right? Or the balancing point is getting doubled. So if we draw a picture, I guess I won't redraw the 1, 3, 4, 5, 7, but the 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 2, 6, 3, 4, 5, 6, 8, 10, 14. So it's kind of like rough sketch of the points. Looks like this. Rough sketch of the histogram. OK, so it's going to balance at 8. The median is also going to be 8. The average and the median are both doubled in this case. So in general, whatever constant you multiply by, the average and the median get multiplied by the same constant. Okay, so in general, average and the median are multiplied by whatever that constant is. If you want to see what happens in terms of summation notation, I'll do that really quick. If we take the average is equal to, sum I equals 1 to n of xi over n. The new average is going to be multiplied by a constant here, right? Cxi over n, I equals 1 to n. And you can kind of see immediately, you can pull that constant out in front. OK, so whatever the average used to be gets multiplied by that constant. You can also see in this that it doesn't matter if the constant's positive or negative. So actually, I guess I erased right here. So if the constant's negative, same effect. Okay, so I'll just say it doesn't matter if constant is positive or negative. OK, so now let's deal with the SD. Questions on that part? Yeah?
What if the mean is skewed to one side?
If the mean is skewed to one side, you're just talking about having a histogram where it's skewed. It doesn't matter. The average is still doubled if I double all the values. It's everything I'm saying is true regardless of whether or not the numbers are, whatever the histogram looks like. Okay? The example I'm doing happens to be where it's symmetrical, but change of scale affects skewed distributions the same way as anything else. Okay? And maybe you could just see that in the formula here. Those xi's could be incomes or whatever. It doesn't really matter. The constant just gets pulled out in front. OK, so let me do SDs, and then I'll do kind of an example that might help illustrate that. Yeah?
Would it change, would your average change
would it change if you had negative numbers in the list? This fact does not change. Some of these xi's could be negative, they could be positive, doesn't matter. The signs of the individual values will change, but the effect on the average won't change. Yeah? Okay, so let me do standard deviation, how that changes with multiplying by either a positive or negative constant. So intuitively, if you double all the values, these are now spread out more than the original values. The deviations from average are doubled in this case. And that's really what you want to think about, I think, is, again, the deviations from average. These are the old ones. The new ones are going to be this. Each value gets multiplied by the constant, and also the average gets multiplied by the same constant, right? This is the effect on the average is that when I multiply all the values by the constant, the average itself gets multiplied by the constant. So the new list of numbers, these values, have an average of c times x bar. And now, this is what happens, right? Whatever the old deviations from average are, they get multiplied by the constant. So now the deviations from average are multiplied by that constant. And when I perform the algebra of taking the RMS, the deviations from average, the constant is all going to come out in front. So that's a little bit messy to show, but like work through all the summation notation of like taking the RMS of all these. So I'll spare you that, but you can see intuitively, the SD measures the typical size of the deviations from average. If the deviations from average get multiplied by a constant, certainly intuitively, the SD should get multiplied by that constant. Okay, as long as it's positive, right? So this is true when C is positive. So if C is negative, I mean, the math is still the same, but the effect on the SD is that it's multiplied by the absolute value of the constant. So SD is multiplied by the absolute value of that constant. So just to sort of say what's going on there, I mean, this is true. What I've written here is true when C is, actually, I'm sorry. Let me say just a little bit more here. So when C is bigger than 0, SD is multiplied by C. That's what's true when C is bigger than 0. Okay, so this equation is true whether C is positive or negative, that the new deviations from average are constant times that deviation from average. If you think about what happens to those deviations from average, the very first thing we do when we calculate the standard deviation is to take the RMS of these. So we're squaring these. So since we're squaring these, the sign of the constant is irrelevant. Okay? So if we multiply by a negative constant, then the SD is multiplied by the absolute value of C. So one way to think about why that's true is that when we square this, we get a positive number no matter what, right? So since we're squaring the deviations from average, regardless of whether or not C is positive or negative, this, when you square it, has to be positive. As a result of that, the standard deviation has to be positive. So it wouldn't make any sense to multiply by the constant itself in this case, because that would give us a negative SD. Okay? RMS, the deviations from average, has to always be positive. Okay? So that's sort of part B, I guess, of the list I had before. That if that constant's negative, the SD is multiplied by the absolute value. Okay, questions on any of that? Okay, so I'll do a couple of quick little examples. Suppose we have a company where the average salary is is $50,000 with an SD of $5,000. And now consider two possible raises that we could give the people at this company. The first one is, suppose everyone gets a $5,000 raise. Okay? So if everyone gets a $5,000 raise, what happens to the average? Goes up by 5,000. What happens to the SD? Nothing. Okay? So the new average is 55,000, and the new SD is still 5,000. Okay? Didn't change. All right, suppose everyone gets a 10% raise. What happens to the average? Sorry? Yeah, the average goes up by 10%. So one way to think about this is like we're multiplying the salaries by what? 1.1, right? If everyone gets a 10% raise, it's like multiplying the salaries by 1.1. It's a positive constant. So average salary is going to go up the same way as before. New average is 55,000. And what happens to the SD? It gets multiplied by the positive constant, right? So before it didn't change. If I just move everyone up by the same amount, just shift everything up to the right, the balancing point is the same, the spread is the same. If I give everyone a 10% raise, one way to think about this is the people that have big incomes get bigger raises, right? In terms of the dollars that they earn, okay? So the big incomes get bigger faster than the smaller incomes. So the net new SD is 1.1 times 5,000, which is 5,500, okay? SD gets multiplied by that constant. So, you know, one way to think about this is the spread of the incomes increases. So the separation between the incomes gets larger. I think this is sort of oops, I spelled everyone wrong, but anyway. I think this is like interesting little quick example to do just because which one would you usually see? The second one, right? Typically, you see raises being given like cost of living increase or whatever. It's always in percentage terms that you tend to see people getting the same percentage raise, which actually has the effect of separating people more, okay? Which you sort of feel like, oh, a 10% raise, that's fair. Well, it depends on what you mean by fair. You are spreading out the incomes a little bit more when you give percentage raises. If you showed the raises that everyone gets, like on paper, showed everyone's salaries and showed the raises, well, you'd see, the people that have higher salaries are getting bigger raises. So maybe that would bother you. But seeing it as a 10% raise feels like, oh, everyone gets sort of getting the same raise. So anyway, okay, questions on that? Okay, let's take a really quick break. I want to get to some other kind of harder examples before we go. So. Okay, let me get started again. I want to get through a couple of examples before I let you go, so let's get going. Okay, so I'm going to play with just this made-up data on toucan beak lengths, just because they're birds that have long beaks. And I'm going to use summation notation to figure out how to deal with what happens to the average in the SD if I take away birds or add birds to my list of numbers. So let me more explicitly say what I mean by that. Suppose we have 12 female toucans, and their average beak length is 20 centimeters. And the SD of the lengths is 3 centimeters. And one toucan flies away. With a beak length of 22 centimeters. So what are average and SD of the remaining 11? So it might feel like you can't do this problem without actually knowing the individual beak lengths. Okay? So without using summation notation, that's sort of true. There's no way to figure out the standard deviation without knowing the actual beak lengths. But I can using the second SD formula that I gave you. So let me do that. Now the average is, I don't know, sort of relatively straightforward here. So the old average is 3 centimeters. And if we want to think about what that actually is, 20 centimeters. So the sum I equals 1 up to 12 of the xi's divided by 12, I know that that's 20. Okay, this is the old average. Old average. So the new average, I can imagine that one of these flies away, so I have the sum of 11 of them. From this, I get that the sum of all 12 xi's, the sum of all 12 beak lengths, is 12 times 20, or 240. So the new average is sum I equals 1 up to 11, xi over 11. So how can I get this? Well, this is the sum of all 12 minus the 12th one that flew away. So this is 240 minus 22 over 11. Okay? So up here, from the average of the original 12, I can figure out what the sum of the 12 is. So that's kind of like if I just stacked up all the beak lengths next to each other, right? I get 240. I take away the 22. That leaves me with the sum of the remaining 11 birds, divide that by 11, and I get an average of 19.8. And you can kind of see intuitively, it makes sense it would go down by a little bit, right? The one that flew away has a slightly longer beak length than average, so the remaining 11 should have a slightly smaller beak length. Okay, questions about that? Okay, so now the SD is kind of messy. But again, I'm going to sort of follow the same basic pattern, which is to write down what I know. I know the old SD. And I'll do this using the second SD formula, and you'll see why, I think, as I go. So I'll just write down the formula first. It's the average of the squared values minus the average squared. And plugging in what I know here, this is actually a sum I equals 1 up to 12 of the squared values divided by 12 minus the average squared. Okay? And I know that that all comes out to be 3. So you notice I know everything in this equation except for the sum of the squares. So if I want to, I can solve for the sum of the squares. Okay? Before I do that, let me just write down what I want. I want the new SD, which is this. Same formula, except now there are 11 squared values. Divide by 11 minus the average of these is 19.8 squared. So what I'd like to know here is the sum of the 11 squared values, right? If I knew the sum of the 11 squared values, I could find out the new SD. Well, I can get that because I know the sum of the 12 squared values, and I know the squared value of the one that flew away, right? So by the same kind of idea here, I know the sum of all the regular values, the actual beak lengths. I can subtract the one that flew away to get the sum of the 11 actual beak lengths. Here, I can use this to solve for the sum of the squared values, subtract 22 squared, the squared value of the one that left, and that's the sum of the squares for the 11. Plug it in here, solve for the new SD. So that's my game plan. And this is not really that different from that in terms of what I'm doing. It's just it feels a little bit messier because there are more numbers floating around, and I'm dealing with the squared values rather than the regular old beak lengths. Okay, but let's do it. So this here, I'll square both sides. So I get sum of xi squared I equals 1 to 12 over 12 minus 20 squared is 400. And I'm squaring the left side, getting rid of the square root, and I'm squaring the right side to give me 9. So 3 squared is 9. And then from there, I add 400 to both sides, and then multiply by 12. So then I get sum of xi squared I equals 1 to 12 is equal to, I'll just write it out kind of longhand, right? I add 400 to both sides, and then I multiply by 12. So that comes out to be 4908. OK? So now from there, like I said, I want to find the sum of the 11 squared values. So the new SD is the sum of the squared values for the 12 minus 22 squared divided by 11 minus 19.8 squared. OK, so I'm just taking that 4908. That's the sum of the 12 squared values, subtracting off 22 squared for the one that left. That gives me the sum of the 11 squared values, divide by 11, subtract off the average squared. So this you can't really do using the other SD formula because the other SD formula deals with the deviations from average, and it doesn't quite work out. So this is something where your life is a lot easier using this formula. OK, so if you do all that math, you get about 3.1. OK? So that's the new SD. OK, any questions about that? Yeah? It's 3 squared. Or it's the 3 up there. I square both sides to get 9, and then I'm taking 400. Yeah. Okay. Yeah. What's your question?
Why does the new SD?
Oh, good. Why does it go up? Well, what was the deviation from average for the bird that left? The original deviation from average is 2, right? This bird is 2 above average in the original list. So that bird's deviation from average is a little bit smaller than the typical deviation from average. The typical deviation from average for the original list is 3. So this bird is slightly closer to average than most of the birds are. So the leftover birds are slightly farther away from the average. So that's why the SD is going up there. OK? Yeah?
How did you get the 4908 minus 22 squared on the 11?
How did I get this? So what I want on top is I want the sum of the squared values for the 11. What I did here to get the 4908 was the sum of the squared values for all 12, right? And one of those values, one of those 12 values that is added up to get that is 22 squared. Because I know that one of those 12 birds has a beak length of 22. Now that bird leaves, so the remaining 11 birds have to have that as their sum of squared values. So that's sum of the squared values, the 11, divide by 11, and crank through. Yeah, make sense? Okay, other questions? Okay. Okay, I'm going to do another one that's similar. And this is, the next example is more kind of typical of what I call on the handout the SD of a long list. So that's at the bottom of the first page of the handout. Okay, so it's going to use a similar technique, but it's, like I say, it's a little bit more what I think about as SD of a long list. Okay, so I want to start with the same 12 birds I had before. So average, or x bar, is equal to 20. The SD is 3. And I want to add in 18 males. And they have an average of 23 with an SD of 4. And I want to find the average and the SD of all 30. Okay. So to find the average of all 30, you might think of this as trying to find the sum of all 30 and then dividing by 30. And you remember when I played with the old average before, this 240 is the sum of the first 12. So if I add to that the sum of the males, the sum of the 18 males, and then divide by 30, that'll give me the average of all of them. So that's kind of my plan for the average. And I'm going to label the males x13 through x30. So I'm thinking about them that way because then I can have a big long list of 30, right? This is x1. If you want, you can think of the females x1 through x12. Let's write that out. Females x1, x2, up to x12. And then the males are going to be x13, x14, et cetera, up to x30. Okay, so that'll look a little bit weird because I'm going to have sums that start from 13 and go up to 30 for the males. But it makes my life a little bit easier at the end because when I combine the two lists, I just have one big long list from 1 to 30. Okay, so that's why I'm doing it that way. All right. So for the males, what I know about the average, the old average, or I don't know, it's whatever. I could just call it the average, I guess. But this is the sum, and I'm going to consider I going now from 13 up to 30 of xi divided by 18. Okay, so that's the way I could write that in summation notation. So if you think about literally what this summation means, it means start when I equals 1, or sorry, start when I equals 13, and end when I equals 30. So that sum on top is x13 plus x14 plus x15, so forth, up to x30, which is exactly what the sum of those 18 males is. Okay, so it looks a little bit strange, but if you just think about what summation does, it starts with this value of I, it ends with that value of I. So it's just adding up those 13 through 30th birds. Okay, so I know that this is equal to 23, right? So then if I want to solve for this, solve for the sum I equals 13 through 30 of xi's, that sum is going to be 18 times 23, which is 414. Okay, so now, for all 30, that's what the average is. Add up all 30 beak lengths, divide by 30. So the sum of all 30 is the sum of the first 12, which I did before over here. Right, the sum of the first 12 females is 240. And then I'm going to add to that the sum of the other 18, which is 414, and divide that by 30. Okay? So again, the top is sort of what you'd imagine if you just stacked up all the beaks one after another. The 12 females add up to 240, and then the 18 males add up to 414. So that comes out to be 21.8. Okay? Questions about that? So if you feel like thinking about why that answer is what it is, first of all, I think it makes intuitively a lot of sense that the average is somewhere in between, right? The average of all 30 should be somewhere in between 20 and 23. And it should be slightly closer to the average of the males because there are more males. Halfway in between 20 and 23 would be 21.5. It's a little bit closer to the males because there are a few more males than females. Okay? So this sort of answer makes intuitive sense, I think. All right. Questions on that? Okay, so now I want to find the overall SD, and this is the hard part, I think. So the overall SD let me just write down what it looks like, and then I'll kind of talk through, like, if you were doing a problem, how you'd figure out to do it this way. Okay, so the overall SD is going to look like this. That second summation formula for SD looks like this. We have that minus the average of 21.8 squared. Okay. So what we'd like to know is find the sum of the squares for all 30, divide it by 30, subtract the average of the 30 squared, take the square root. That gives us the overall SD. Okay, so that's our formula. So again, just like in the previous problem, what we really want to know in the problem with the one that flew away, we want to know the sum of the squares for all these birds that we're interested in. And you notice that in the previous problem, I found the sum of the squares for the, actually, I'm sorry, I want this one. The sum of the squares for the 12, right? This is the sum of the squares for the first 12 birds. If I added to that the sum of the squares for the males, then I'd have the sum of the squares for all 30. Okay? So if you imagine what this is just x1 squared plus x2 squared plus x3 squared up to x12 squared. If I find the same thing for the males, it's x13 squared plus x14 squared, so forth up to x30 squared. Add them together, and I just have this big, long sum of squares, x1 squared all the way up to x30 squared. Okay? So essentially, I'm going to do the same math that I did there, right? There, I did it for the females and for the males. I know the SD is this formula. So again, this is this slightly strange summation from 13 to 30. Xi squared divided by how many there are, which is 18. Subtract 23 squared. I know that comes out to be 4, right? I told you the SD for the males at the beginning of the problem is 4. All right, so from this, I know everything except for this sum of squared terms, so I can crank through and solve for that. So squaring both sides, I get sum I equals 13 to 30 of xi squared over 18 minus 23 squared is equal to 4 squared, right? Squaring both sides. And then again, I'm going to kind of throw everything on the other side to solve for that sum of squares term. I equals 13 to 30 of xi squared is equal to 4 squared plus 23 squared times 18. Okay? So I'm adding 23 squared to both sides and then multiplying by 18 to solve for that sum of squares. Okay? So that comes out to be 9,810. So questions about that? What I did to get to that sum of squares term. Okay, so almost done. I have the sum of the squares for the females. I have the sum of the squares for the males. So if I add that together, I'll get the overall SD. So I have 4908 plus 9810. Again, that's sum of the squares for the first 12, sum of the squares for the other 18, females, males. Divide by 30. Subtract the overall average of 28.8 squared. 21.8 squared. And that comes out to be 3.9. Okay, so that's something in between 3 and 4. That gives you the overall SD. Before I realize people want to try to pack up. It's almost time to go, but I do want to say a couple words about how to do these problems. Like in practice, you see these kinds of summation problems. There are some of them on the homework for Monday. And what you want to think about, I think, is think about, OK, what is it that I want to find? So in this case, I wanted to find the overall SD. And I know everything except for that sum of squares term. Then think, OK, where can I find the sum of the squares? Well, SD formula has the sum of the squares. So if you can find the separate SDs and find the sum of the squares for each group separately, then you can combine them into the sum of the squares for this whole long list. Okay, so that's kind of the logic of this SD of a long list method, is to get the sum of the squares separately, combine them, and then get the SD of this whole list. So there's two different things going on here. One of them is combining two lists. One of them is what happens if one thing leaves, if one bird leaves. Then we have to subtract it from the sum of the squares. OK, questions? Yeah. Yeah, for the first one, the average is 19.8, right? This is the average of the 11, right? This is the average of the 11. Here, I want the average of the 12. For all the females, I want the average of all 12 birds, which is 20. Right? This 23 is the average of the males. Maybe come up and ask me. If anyone has any questions, I'll stay for a couple minutes.